Christmas Day, 1642. In the cold, rural quiet of Woolsthorpe Manor, a child is born premature, small enough to fit inside a quart mug. His father, an illiterate yeoman, is already dead. This frail infant, hovering between life and death, is Isaac Newton. From his very first breath, he is a figure defined by absence and isolation, a solitary spark in the Lincolnshire winter.
His mother remarries and abandons him to the care of a grandmother. The psychological scar is immediate and permanent. Young Isaac grows into a resentful, introspective boy, utterly failing as a farmer. He ignores the straying sheep to build mechanical windmills and water clocks, preferring the predictable laws of beers to the chaotic affection of humans.
Rescued from the plow by a perceptive uncle, he enters Trinity College, Cambridge in 1661. He is a subsizer, earning his keep by emptying chamber pots for wealthier students. While the curriculum peddles Aristotle's ancient errors, Newton keeps a secret notebook, the Questionnaires, scribbling a mantra that would define the scientific revolution. Plato is my friend, Aristotle is my friend, but my best friend is truth.
Then the Great Plague of 1665 strikes. The Black Death descends upon London, and the university closes its gates. Newton is forced to retreat back to the rustic silence of Woolsthorpe. To the outside world, it is a time of horror and stagnation. For Newton, it becomes the Annus Mirabilis, the year of miracles.
In the total isolation of the countryside, untethered from academic dogma, his mind explodes. Within 18 months, a 23-year-old recluse will lay the foundation for modern science. He works in a state of near-manic obsession, often forgetting to eat or sleep, driven by a divine hunger to decode the syntax of God's creation.
First, the mathematics of change. To calculate the slopes of curves and the areas under them, he invents the method of fluxions, what we now call calculus. He solves ancient riddles of motion and accumulation, creating a mathematical language that can describe the dynamic universe. Yet, he tells no one, locking the discovery away in a wooden chest. Next, he turns to light. The prevailing theory is that white light is pure, and colors are modifications of it. Newton bores a hole in his window shutter, allowing a single beam of sunlight to pass through a glass prism. He proves that white light is not a singular entity, but a composite of all colors in the spectrum. He literally unweaves the rainbow. Then comes the legend, the apple. While the story of it hitting his head is likely an embellishment, the insight is real. Looking out into the orchard, he watches an apple fall and looks up at the moon. The question forms, does the force that pulls the apple to the ground also reach out to the heavens to hold the moon in its orbit?
It is a heretical thought. Before this moment, the heavens were considered a separate realm, governed by different laws than the earth. Newton dares to unify them. He calculates the inverse square law, realizing that gravity is a universal force, an invisible tether binding the cosmos together. The apple and the moon obey the same master.
But there is a shadow side to this genius. Newton is not just the first scientist, he is the last of the magicians. Parallel to his physics, he dives into alchemy. He spends sleepless nights tending furnaces, inhaling toxic mercury fumes, searching for the philosopher's stone. To him, gravity and alchemy are parts of the same quest, to find the active spirit of God in matter.
His personality is as complex as his math. He is paranoid, neurotic, and deeply vindictive. He fears plagiarism so intensely that he refuses to publish his findings for decades. He views his discoveries not as contributions to mankind, but as private communions with the divine, secrets he is reluctant to share with little smatterers in mathematics.
When the plague recedes in 1667, he returns to Cambridge, transforming from student to fellow, and soon the Lucasian professor of mathematics. He carries with him the secrets of the universe, hidden in his luggage. The world has changed forever, but the world doesn't know it yet.
He constructs the first reflecting telescope, a practical application of his optical theories.
It is this small, powerful instrument that finally brings him to the attention of the Royal Society. But even then, criticism from rivals like Robert Hooke drives him into a rage. He threatens to burn his papers and withdraw from society entirely.
The Miracle Year was a burst of unparalleled intellectual violence. In a single stroke, Newton set the stage for the Enlightenment. He provided the tools to measure the infinite and the laws to predict the future of celestial bodies. Yet for now, the Principia Mathematica remains unwritten, existing only as fragmented notes in a chaotic mind.
Isaac Newton stands on the precipice of history. The solitary child has become the master of the physical world, but the battle to publish his work, to defend his priority, and to reshape human understanding is just beginning. The miracle year is over. The era of Newton has begun. 1665, the Great Plague ravages London, turning the bustling city into a graveyard. While society collapsed, a young Isaac Newton retreated to the safety of Woolsthorpe Manor. It was here, in isolation, that the Annus Mirabilis began, a year of wonders that would rewrite the laws of nature.
Newton turned his bedroom into a laboratory. At the time, scholars believed white light was pure and modification created color. Newton, skeptical of the ancients, bored a tiny hole in his window shutter to admit a single circular beam of sunlight.
He intercepted the beam with a triangular glass prism. Instead of merely brightening, the light fanned out, painting an oblong spectrum of vivid colors on the opposite wall: violet, indigo, blue, green, yellow, orange, and red. Critics argued the prism itself colored the light. To disprove this, Newton performed the experimentum crucis. He isolated the red band through a board and passed it through a second prism. It did not change into other colors. It remained stubbornly red. This led Newton to a radical conclusion. White light is a heterogeneous mixture of all rays. He visualized light not as waves, but as a stream of particles, corpuscles, bombarding the retina. This theory would spark a bitter, lifelong feud with Robert Hooke. His understanding of optics revealed a flaw in refracting telescopes. Glass lenses inevitably separated colors, blurring the image. To fix this, Newton abandoned lenses for mirrors, grinding his own metal alloy to create the first functional reflecting telescope. In 1671, the Royal Society examined his invention. It was a sensation. A device 6 inches long could magnify as much as a refractor 6 feet long. It cemented his reputation, but the ensuing debates drove him back into his shell. While mastering light, Newton wrestled with motion. The mathematics of the time could calculate average speed, but failed to describe the speed of an object at a single, specific instant in time. The geometry of the Greeks had hit a wall. Newton's solution was the method of fluxions. He treated mathematical quantities as flowing, changing over time. By calculating the rate of change, the fluxion, he invented what we now call differential calculus. He discovered the fundamental link. Finding the slope of a curve and calculating the area underneath it were inverse operations. This realization gave humanity the language to describe how things change, from the orbit of planets to the flow of fluids. Yet, paralyzed by a pathological fear of criticism, Newton kept his calculus a secret. He locked his papers away in a chest, writing his findings in anagrams to claim priority later, without revealing his methods to potential rivals. This secrecy led to the greatest dispute in mathematical history. German polymath Gottfried Wilhelm Leibniz developed calculus independently years later. Newton, enraged, used his presidency of the Royal Society to accuse Leibniz of plagiarism. Newton's optical work, Optics, wasn't published until 1704, only after his rival Robert Hooke had died. He waited decades to release his findings, ensuring the last voice heard on the matter would be his own. Today, Newton's calculus is the bedrock of modern engineering and physics. Without the tools he forged during the Plague Years, the Industrial Revolution and the Space Age would have been impossible. In the quiet of Woolsthorpe,
Newton had split the light and sliced time itself. But his greatest synthesis was yet to come. He was preparing to decode the invisible force that bound the apple to the earth and the moon to the sky. In the cloistered silence of Cambridge, 1684, a mental storm was brewing that would sweep away 2,000 years of Aristotelian physics. Isaac Newton, a recluse prone to paranoia, sat within the walls of Trinity College, guarding secrets that defined the very fabric of reality.
The catalyst was a visit from Edmund Halley, a young astronomer seeking to settle a bet made in a London coffeehouse. He asked Newton, if gravity pulls with an inverse square force, what is the shape of a planetary orbit? Newton replied instantly, an ellipse. I have calculated it.
But Newton could not find the proof. Fearing his rival Robert Hooke would claim credit for the inverse square law, Newton retreated into absolute isolation. For 18 months, he barely ate or slept, consumed by a fire to mathematically prove the mechanics of the cosmos.
What emerged was the Philosophiae Naturalis Principia Mathematica. He began by defining the undefinable, mass, force, and momentum. He stripped the universe of occult qualities and reduced nature to measurable quantities.
His first law of motion shattered the ancient belief that objects naturally stop. Newton declared that an object in motion stays in motion forever unless acted upon by a force, the principle of inertia. The second law gave us the most famous equation in mechanics: force equals mass times acceleration. It provided a computational tool to predict the motion of everything, from a falling apple to a cannonball.
The third law introduced perfect symmetry. For every action, there is an equal and opposite reaction. Nature was no longer chaotic. It was a balanced ledger of forces.
But his greatest leap was universal gravitation. Newton dared to propose that the force pulling an apple to the ground was the exact same force holding the moon in its orbit. He united the terrestrial and celestial realms under one law.
To prove this, he utilized the geometry of the ancients, deliberately avoiding his own secret invention of calculus, to ensure the book would be accepted by the conservative scholars of Europe.
The writing process was a physical ordeal. Newton's hair turned gray, and he often forgot to dress. He was channeling the mind of God, seeing the universe as a giant clockwork mechanism.
Yet the Royal Society was bankrupt, having spent its entire budget on a flopped book about the history of fishes. They could not afford to publish Newton's masterpiece. Edmund Halley stepped in as the hero of this story. He not only edited the manuscript and soothed Newton's feuds with Hooke, but paid for the printing out of his own pocket. In 1687, the Principia was released. It was dense, difficult, and written in Latin. Few could understand it, but those who did realized that the world had irrevocably changed. Newton had provided the mathematical blueprint for the Industrial Revolution. He showed that nature was not governed by the whims of spirits, but by precise, predictable laws.
With the Principia, Isaac Newton became the supreme architect of the physical world. He had stolen the secrets of the gods and written them down in the language of men. To the world, Isaac Newton was the paragon of the age of reason, the father of modern optics and gravity. But in 1936, a metal trunk auctioned at Sotheby's shattered this pristine image. Inside lay thousands of pages, not of mathematics, but of coded madness and mysticism.
Economist John Maynard Keynes, who acquired these papers, famously declared that Newton was not the first of the age of reason, but the last of the magicians. For 30 years, while the world celebrated the Principia, Newton led a double life.
Deep within the walls of Trinity College, away from the prying eyes of the Royal Society, Newton built a secret laboratory. Here, the furnaces burned continuously, sometimes for weeks, as he chased the ultimate prize of the Hermetic tradition, the Philosopher's Stone.
He wrote over 1 million words on alchemy, a heresy punishable by death or imprisonment in 17th century England. His manuscripts were not meant for publication. They were private conversations with the ancients, written in elaborate ciphers,
to hide his findings from the unworthy.
Newton believed that Greek myths were actually encoded chemical recipes. He spent decades translating the Emerald Tablet of Hermes Trismegistus, convinced that a secret wisdom, the Prisca Sapientia, had been lost to mankind and needed to be rediscovered.
His primary obsession was the net, a method to catch the spirit of the world. He sought the philosophical mercury, a substance he believed could dissolve all metals and allow them to vegetate and grow, bridging the gap between inanimate matter and life.
In his notebooks, he drew the Star of Regulus of antimony, a crystalline formation produced during the purification of ores. To Newton, this wasn't just chemistry, it was a signpost on the road to divinity, a physical manifestation of God's architecture.
The danger was physical as well as legal. Newton frequently tasted his own concoctions. He worked with arsenic, lead, and immense quantities of mercury. He was literally poisoning himself in pursuit of hidden truth. Modern analysis of a lock of Newton's hair revealed mercury levels 40 times the natural average. This toxicity likely precipitated his infamous breakdown of 1693, a year of paranoia, insomnia, and tremors, where he accused his best friends of trying to embroil him with women. Yet these alchemical pursuits were not a waste. They were the crucible for his physics. The concept of gravity, a force acting across a vacuum without physical contact, was an occult idea rejected by the mechanical philosophy of Descartes. Newton dared to propose action at a distance precisely because his alchemical worldview allowed for active principles in matter. While his rivals saw a clockwork universe, Newton saw a living one, animated by the will of God. He also applied his obsession with codes to the Bible, calculating the apocalypse. He spent as much time on the dimensions of Solomon's temple as he did on the calculus, believing the temple's blueprint held the harmonic ratios of the universe.
Upon his death, his family, horrified by the heretical nature of his private writings, suppressed them. For 2 centuries, the alchemical Newton was erased, leaving only the rational scientist the Enlightenment wanted to see.
It was only through the survival of these papers that we now understand the unity of his mind. There was no separation between his science and his religion. The telescope and the furnace were 2 tools for the same job, decoding the mind of the Creator. Newton remains a giant of science, but he was also a sorcerer in search of the divine. His legacy is not just the laws of motion, but the relentless, sometimes dangerous, pursuit of the absolute truth by any means necessary.
In 1696, Isaac Newton left the quiet, contemplative cloisters of Trinity College for the chaotic, smog-choked streets of London. He accepted the post of Warden of the Royal Mint, a role traditionally viewed as a gentle retirement for accomplished gentlemen, a sinecure requiring little more than a signature. The establishment expected a figurehead. Instead, they received a force of nature.
Newton arrived at the Tower of London to find the nation's currency in absolute ruin. The silver coins of the realm were being clipped, sheared around the edges for their raw metal, reducing their value by half and threatening to collapse the English economy. It was a crisis of mathematical proportions, and Newton approached it not as a bureaucrat, but as an alchemist, purging impurities from a base metal. He immediately rejected the passive role of his predecessors. The author of the Principia Mathematica applied his terrifying intellect to the machinery of state. He reorganized the mint with factory-like precision, calculating the exact motion of men and machines to maximize coin production, increasing output by tenfold in a matter of months. But efficiency was only half the battle. The other half was war against the counterfeiters. These coiners were not merely criminals. In Newton's eyes, they were traitors, subverting the king's authority. His chief antagonist was William Chaloner, a flamboyant genius conman who had grown rich mocking the law and forging the nation's wealth. Chaloner made a fatal error. He underestimated the obsessive nature of the warden. Newton transformed himself into a relentless detective. He had spent years hunting for the secrets of the universe. Hunting men proved to be a simpler, albeit grimier, equation. Historical accounts suggest Newton went undercover, donning the disguises of habits of ordinary drapers and porters. He descended into the hellish underworld of London's gin shops and taverns, the very places a man of his standing should never be seen, all to gather intelligence on the coining rings.
He built a vast network of informants, paying out of his own pocket to bribe thieves and turncoats. The scientist who defined gravity now pulled the strings of a complex web of espionage, documenting every whisper and confession with the same rigorous detail he applied to his optical experiments.
Newton became a terrifying inquisitor. Between June 1698 and Christmas 1699, he conducted over 200 cross-examinations personally. He was known to intimidate suspects, leveraging the fear of the gallows to extract the truth, meticulously separating lies from facts until the logic of their guilt was undeniable.
Challoner, arrogant to the end, believed he could outwit the mathematician. He petitioned Parliament, accusing the mint itself of corruption. It was a bold gambit, but Newton waited, gathering irrefutable proof, closing the variables one by one until Challoner had no room to maneuver. The trap snapped shut in 1699. Newton's agents raided Challoner's operation, seizing the copper plates and heavy presses. The evidence was mathematical in its certainty. Challoner was dragged to Newgate Prison, the hell above ground, to await the warden's justice. At the trial, Newton was ruthless. He utilized his informants to dismantle Challoner's defense piece by piece. There was no mercy, no philosophical abstraction. To Newton, counterfeiting was high treason, a direct violation of the cosmic order he sought to uphold on Earth. William Challoner was sentenced to be hanged, drawn, and quartered. From his cell, he wrote begging letters to Newton, pleading for his life, appealing to Newton's Christian charity. Newton did not reply. The equation had been balanced. On March 22, 1699, Challoner was dragged to the Tyburn Tree and executed. Newton did not attend. His duty was discharged. He had successfully sent 28 coiners to the gallows during his tenure, proving that the mind which unlocked the heavens could also master the gutter.
Newton's ultimate victory was not just in the hangings, but in the design. He oversaw the introduction of milled edges on coins, grooves that made clipping impossible without detection. It was a technological solution to a criminal problem, a standard still used in currency today.
The master of the mint had saved the British currency. This period revealed a darker, harder side of the genius, a man who could not only conceive of the laws of motion, but could enforce the laws of men with terrifying, absolute rigidity.
If I have seen further, it is by standing on the shoulders of giants. This famous line, penned in a letter to Robert Hooke in 1676, is often cited as the ultimate expression of scientific humility. Yet history suggests it was likely a double-edged sword, a subtle jab delivered by a man who saw few equals.
Robert Hooke, Newton's fiercest rival and a man reported to be hunchbacked and short of stature, had tormented Newton's early career. Many historians argue the giant's remark was a cruel, sarcastic reference to Hooke's physical deformity, implying that Newton didn't need Hooke's help to see the stars.
By 1693, the relentless pressure of his intellect caused a fracture. Newton suffered a severe nervous breakdown, a black year characterized by paranoid letters to friends like John Locke and Samuel Pepys, accusing them of conspiring against him. The mind that organized the cosmos was for a time in chaotic disarray.
Seeking a departure from the isolation of Cambridge, Newton moved to London to become the warden and later master of the Royal Mint. He did not treat this as a ceremonial retirement. He approached the currency crisis with the same rigor he applied to gravity, overseeing the great recoinage that saved the British economy. He became a detective, hunting down counterfeiters with ruthless efficiency. He built networks of informants in the London underworld, personally interrogating suspects. His pursuit of the notorious counterfeiter William Challoner ended with Challoner's execution at Tyburn, a grim testament to Newton's administrative iron fist. In 1705, Queen Anne visited Trinity College, where she bestowed a knighthood upon him. Sir Isaac Newton became the first scientist to be knighted, not for his Principia, but largely for his political service and work at the Mint,
solidifying his status as a national icon. As president of the Royal Society for 24 years, Newton ruled as an autocrat. He moved the society to Fleet Street and famously presided over the erasure of Robert Hooke's legacy, allegedly destroying Hooke's only portrait, ensuring his rival would vanish from history.
His later years were consumed by the calculus controversy. Gottfried Wilhelm Leibniz had developed calculus independently, but Newton accused him of plagiarism. Newton anonymously wrote the Royal Society's report that officially condemned Leibniz, acting as both accuser and judge in his own case.
When he died in 1727, he was accorded a state funeral, the likes of which had never been seen for a subject. He was buried in Westminster Abbey, resting among kings. Voltaire, present at the funeral, marveled that England honored a mathematician as other nations honored a conqueror. But the true complexity of his mind remained hidden in a trunk of papers discovered centuries later. In 1936, economist John Maynard Keynes purchased these writings, revealing that Newton had written more on heresy and alchemy than on physics. Keynes famously declared, "Newton was not the first of the age of reason, but the last of the magicians." Despite his obsessions with the occult, his mechanical universe laid the groundwork for the Industrial Revolution. The laws of motion allowed engineers to build the machines that would define the modern world. Every gear, piston, and rocket follows the script Newton wrote. Albert Einstein, who would eventually overthrow Newton's concept of absolute time and space, kept a picture of Newton on his study wall. He knew that without the static, predictable universe Newton defined, the theory of relativity could never have been conceived. Newton's legacy is a synthesis of the divine and the empirical. He sought God in the numbers, believing that by decoding the laws of nature, he was reading the mind of the Creator. To him, the Principia was a form of worship. He was a man of paradoxes, a recluse who sought fame, a Puritan who managed the nation's wealth, and a scientist who spent nights trying to turn lead into gold. His humanity was as flawed as his mathematics were perfect. Isaac Newton changed the world not by removing the mystery, but by proving that the mystery had rules. He showed us that the universe is knowable, provided one has the courage and the arrogance to ask the right questions.